Okay, good morning, good afternoon, everybody.
Good afternoon, sir.
Good afternoon, sir.
Good afternoon, sir.
See. So, our last class was on the 31st. So, I guess I should wish everybody a Happy New Year. So, Happy New Year.
Happy New Year, sir.
Yes,
Happy New
Year,
Year, sir.
sir.
Same to
Same to
you.
Okay.
Happy New Year, sir.
Now, in the last class, I showed you one derivation of Lorentz transformations, right? And again, if some of you would please turn your video on, it's helpful to have that visual feedback. Okay, so what happened? Yeah. Okay, audio is not updating. Okay. Okay, so I've given you one derivation of Lorentz transformations. Now, thing is that there is more than one way to derive Lorentz transformations, right? So if you just search for Lorentz transformation derivation on Wikipedia, or you look in the on Google and you search, or you look in the Wikipedia article, you'll find there are about 5 or 6 different ways to do the derivation. Okay? But the end point is that, right, you have this so let's write that down again. X prime is equal to x minus mu naught t 1 minus mu naught t square, t prime is equal to t minus 1 square, right, where you have some frame of reference O, which has some coordinates x and t, and you have some frame of reference O prime, who has some coordinates x prime and t prime, and for the sense of this equation, O is moving with respect to O prime with some velocity, V naught in the positive x direction, right? So if you want to switch to if you want to ask, well, what is the transformation as seen by O, that means you want to find the relationship between the x and, you want to find x as a function of x prime and t prime, and t as a function of t prime comma t prime. So this symbol colon followed by an equal sign means that you define x to be, and this is a function of x prime and t prime, right? Then principle of relativity tells you that the only change that really happens is that with respect to O prime is moving in the opposite direction with a speed minus v naught, right? So what would be the relationship between the coordinates in that case? Be x plus v naught t times gamma t is equal to, right? Gamma remains the same because gamma only depends on v naught. Okay. And so last time I mentioned to you that this Lorentz transformation can be thought of as a hyperbolic rotation. It is a hyperbolic rotation. And what are the coordinates? Your coordinates are x prime and ct prime. Why do we multiply by c? So that the dimensions of ct are equal to the dimensions of length, which is L, right? So these two quantities are on the same footing. That's the reason why we multiply by C. And if we write this in this way, and we, instead of V naught, we use beta, which is the ratio of V naught by C, right? Then we can write x prime ct prime xt. We can write this, so we have 1 minus, so what is the expression for beta and all that? So this is quotient. So gamma becomes quotient of theta, beta gamma becomes sinh of theta. And if you look in the relationship for x prime, this is x multiplied by gamma, right? And then in this expression, if you multiply and divide by c, you get minus beta gamma. So this becomes cos theta minus sin theta. And then in this expression, you have for the x term again minus beta gamma. So you get minus sin theta cos theta. So if you look at it this way, this is a hyperbolic rotation. And what is the other property of this hyperbolic rotation is that if you have any two events in space-time, so as I explained in the previous class, an event, right, is a position along with a time, right? So imagine that now this is your frame of reference. Let's say this is O. Right, so this is the O frame, this is X and this is CT. Now in O's frame of reference, there are two flash bulbs that are located at, let's say, plus L, L naught and minus L. Okay. And this is the vertical axis, is the time axis, right? So first of all, if we want to ask, for instance, let me make this different color, let me make it green. If we want to ask, let's say, what is the surface of constant position, right? So this is the, sorry, constant time. So this is the surface of constant time, right? This line. This line is the surface of constant time. It corresponds to CT prime is equal to 0. Okay. What about the other surfaces? Well, the other surfaces, these are the surfaces of constant time, right? CT prime is equal to, let's say, C times delta t, and let's say this is 2 delta t. And then similarly, we can go in the past, right? And make this minus delta t and minus 2 delta t. So these are the surfaces of constant time, right? Similarly, I can ask what are the surfaces of constant position, constant x, right? So those surfaces will be what? It will be these straight lines. Okay. So this is what the first line in the center is x is equal to 0. This line we can say is delta x. This is 2 delta x. And in exactly the same way, my lines are not coming out very straight, but that's okay. This is minus delta x and this is minus 2 delta x. Okay. Now, these two lamps are located on my surface of constant time at a distance of plus L0 and minus L0. Okay. And what do these lamps do? They emit a beam of light. Now, when light is emitted, what is the velocity of light? C. Right. So C is equal to what? Delta x by delta t, right? So if I multiply, what about velocity? Velocity is also delta x by delta t. Now, what if I take v by c for any object, right? V by c is delta x by c delta t, right? What is this? This is beta, right? So if I look at this diagram again, x and ct, okay, then what is the trajectory of an object which is moving in a straight line look like? Well, first of all, what is the trajectory of an object which is stationary? Something is over here at some position L0 and it's stationary, right? What will be its trajectory? So it's not moving in the x direction, right? But there will be a quote unquote motion in the time direction for stationary objects also, right? So you can say that at every point in space, you can imagine that there is a clock. At every point in space. Okay. And these clocks never stop ticking. Okay. This is one way to think of it. So if you have a clock, right, if you think about the ticking motion of a clock, the ticking motion is like the change that is happening in the system. So if you have a clock over here, it shows 12 p.m. After some time, it will show, let's say, 12:30 p.m. After some time, it will show 1 p.m. right? 1:30 p.m. and so on. So even if the object is not in motion, right? And now you can remove the clock. Even if you don't have a clock, you just have a piece of stone that is sitting there. Well, that piece of stone will also keep moving in time, right? Whatever it is, it doesn't matter what it is. It's a living object, a dead object, it doesn't matter. So this is what we call the trajectory, or there is a word for it. This is called the whirl line of an object or a particle or whatever, or a system, right? Because whatever this thing is, we don't know what it is. It could be another spaceship, it could be an atom, it could be anything. And so this line, this trajectory is called the whirl line of this of this object. Okay. If people have any doubts at any point in time, please stop and ask me. Unmute yourself and ask me. Okay. Zoom has disconnected me again. All right. So now we can ask the same question. What happens if my system is moving, right? If this object is moving in as seen by this O frame of reference, right? And for simplicity, we will say that the position of an object. So now we have a moving object. Right? Moving at some constant velocity v. And for simplicity, we will say that the position x is 0 at time t is equal to 0. Okay. So what will be the motion? What will be the word line of this object? Anybody? How would I draw that line?
That would be like a slant line, sir, with some slope.
Right. But what can you say about the slope of that line?
It's positive.
It could be negative also. It could, if it's
It
going
could
in,
even move the other way. Yes, sir.
it could be going in this direction, or it could be going in this direction.
But it couldn't go down as the time is not negative.
Sure, it could go in the back also. Okay, it'd be an object moving in towards the past. This is the thing. Okay, this is what happens. So when you actually talk about antiparticles, for instance, it turns out that antiparticles are best thought of as particles moving backwards in time. But don't worry about all of that just now. Okay. Now, what will be the slope of this line? If you look at any 2 points on this line, if I look at 2 points, right? And then I ask, well, what is this? This is delta x, right? And what is this interval? This is c delta t, right? And then you have some angle theta. So tan theta is what? C delta t divided by delta x, which is c divided by v naught. What is that? That is equal to 1 by beta. Right? Is this fine? So
Yes,
the
sir.
slope of the line m is equal to 1 by beta. Okay. Now, what is beta for light? For something moving at the speed of light?
1.
1.
And what angle would that correspond to?
45 degrees.
45 degrees. Right. So if you have any line in this diagram, if you draw any line at an angle of 45 degrees, right? This is my best attempt at drawing a 45-degree line. This corresponds to something that is moving with the speed of light. Okay. And if I have any line which is at an angle greater than 45, that means its velocity is less than the speed of light. And if I have any line, let me try to find a nice color. Don't really have too many options. If I have any line which is has a slope less than 1, then its velocity is greater than the speed of light. Right? So for all physical objects, right? All physical objects will be drawn as angles, lines moving at an angle of 45 degrees or less. Right? Okay, so these diagrams, these are called space-time diagrams. Also known as Minkowski diagrams. In honor of there was a mathematician called Hermann Minkowski who gave this space-time picture of relativity some years after Einstein's papers in 1905. So these are called Minkowski diagrams of space-time. Okay. Now let us come back to this picture of now that we know what these lines represent. Okay. Now let me come back to that to this situation that I had earlier, which was that you have two objects which are located at equal displacements from the origin on a surface of constant time. Okay. And what happens is that these are two lamps, let's say. Okay. And they emit a flash of light at time t is equal to 0. Now, what will be the angle at which the light will travel? So if I draw the light, a beam of light which is going out from this point, what will it look like?
It will be with an angle of 45, sir, as it's light.
And what will be the intersection with the x-axis?
It will be at minus L. With the y-axis, it's minus L.
Well, with the x-axis, its intersection will be just this, right? So this is the beam of light. Similarly, the same beam of light is emitted by the other one at the same time, right? So it also travels at a 45-degree angle. Right? Now, what can you say about the location on the y-axis at which these two beams will intersect the y-axis? Right? This beam and this beam, they will intersect the y-axis. What can you say about that location?
L0.
Huh?
At distance L0.
They will intersect the y-axis at the same point, right? So again, this is they will both meet here at the same point, right? Why? Because
Both are
What is this?
equidistant.
Both are equidistant. M is equal to 1, M is equal to 1. Delta X is the same. So delta T, C delta T will also be the same, right? So from the perspective of the observer, so let's say the observer is now, who is this observer? This observer is, let's say, sitting in this is the observer, and this is the frame of reference O. And there is a train car whose length is 2L0. And these two light bulbs are located on either end of the train car, and they emit this beam of light, right, at some time t, which is the same as seen by both of them, as seen by this observer. And when those photons reach this observer, they will reach simultaneously, right? So here you have simultaneous arrival. I hope you can see my writing, it's a little small, of photons, right? So this word simultaneous is important, right? It means something. It means something that happens at the same time, right? Okay. Now I have another observer, O prime, right? And this is a train car, right? So let me say that this train starts moving with some velocity v naught in the positive x direction as seen by O prime. Okay, and O prime is some person, let's say, standing on the station platform where the train is located. Right? What does O prime see? The question is, what does this guy O prime see the light signals arrive at the same instant of time at the center of the train?
No, sir.
And the answer is no. Okay. So let us ask ourselves why that should be the case. So let us look at the whole picture from the perspective of O prime. Okay. So now we'll draw another space-time diagram. But now this is the O prime frame of reference. Okay. All right. Now, according to O prime, what does the trajectory of O look like in O prime frame of reference? How do I draw O? O is somebody who is moving, right? At some constant velocity with respect to O prime. So how do I represent that in this diagram? Answer should be, should be obvious,
With 2
right?
points, with 2 points of between distance to element.
Well, with just 2 points. You have some moving object, right?
Yes, sir.
How do I represent a moving object? Just with 2 points. We just talked about this like a few minutes ago, right?
Like, we draw 2 lines, sir, as
We
inclined lines.
have one line, right? We have one line which represents the trajectory of that system. We have one line, that's it. So O, as seen by O prime, let's say we are looking at the position of this observer as seen by O prime. Then the position of this observer will, let's say, be on some line like this, right? I'll use a different color. I'll use orange lines. This will be O. And I'll use orange lines to denote speed of light, okay? Now, what can you say about the speed of light in this frame of reference?
With the same.
This is light, right? These are beams of light. They are moving with the speed c as seen by O.
But by order, I should C plus V naught and C minus V naught.
No, we are working with relativity now, right?
They will be the same speed of light. Won't
So
change.
as seen by O prime also, these beams are moving at the same light, same speed.
Same speed.
So how would I draw it in the diagram? I would draw them
Again by a
as
45-degree.
45-degree lines, exactly. All right. Okay. And what is this green line that I have drawn, right? This is O's world line, right?
Yes, sir.
Yes.
This is O's world line. Now look at the earlier picture. In the earlier picture, this is the O frame of reference, right? And I have the observer O located at the origin, right? This guy. Now, what is the word line of this observer in their own frame of reference?
A point. I mean, a straight line.
It just looks like this, right? It's just the constant. Space is a constant, but time keeps moving. It's just like the stationary observer, right? So in your own frame of reference, right, any observer is at rest in their own frame of reference. Right? So this is the word line of the observer O in O's frame of reference, right? What is the word line of this observer in O prime's frame of reference? It's this green line. So as seen by O prime, what is this observer doing?
Moving.
Moving along this line, right? And I'll make this guy green to make the colors similar. Okay. Right. So this is the constant position axis. Right. So this is the time axis of O. And this is also the time axis of O as seen by. So what is this? This is CT, right? This is the time axis of O as seen by O prime.
Oh,
Right. So if I take any point here which corresponds to some time interval, right? Delta t, 2 delta t, 3 delta t, right? So on. That point will correspond to some point here, right? Let's say delta t, 2 delta t, 3 delta t, right? Venu, just mute yourself if you're not if you're not answering a question or something, okay?
Okay, sir.
Right? But as seen by O prime, this will be some delta t prime. This will be some 2 delta t prime. Okay. And this will be some 3 delta t prime. Right? So this is this word line picture. So I want you all to just look at these pictures and understand how we are drawing different observers. Okay. Now I can also ask the same question from the perspective of the Lorentz transformation. What does the Lorentz transformation tell me? It tells me that T, right? So T is equal to T prime plus V naught x prime by C square times gamma, right? So this is the time of the observer O as seen by the observer O prime, right? Now I can ask, and what is the position? X is equal to x prime plus V naught T prime times gamma. Now what is this line? This line corresponds to the equation x is equal to 0, right? That is what this line is, x is equal to 0. So x is equal to 0, if I say x is equal to 0, what does that imply in terms of the prime coordinates? It implies that x prime
is equal to minus V naught.
plus V naught T prime by gamma, sorry, not by gamma, times gamma is 0, which tells me that this x prime divided by C T prime is equal to minus V naught by C. Right? So I'm getting some sign error, so maybe I'll just take these guys and put a minus sign here. Minus sign and then get plus sign. So as seen by O prime, the time axis of O looks like this line. All right. What about the space axis? Now the space axis corresponds to what equation? It corresponds to T is equal to 0. Right. So if I say T is equal to 0, what happens to the time axis in the prime coordinates? This means that this equation is equal to 0. So T prime minus V naught x prime by C square gamma is 0, which means T prime Ct prime is equal to V naught by C x prime. Now what is x prime by Ct prime? This is beta. So this becomes 1 by beta. Okay. So what is the slope of this line? The slope of this line, this CT line, the slope of this line is m is equal to beta, where beta is equal to V naught by C. Right? What about the constant time surface? The constant time surface is a line which has a slope of 1 by beta. right? Now beta is less than 1, so 1 by beta will be greater than 1. So how will I draw that line? It will look like this. This is the x-axis of the O observer, and m is equal to 1 by beta. And if I extend it in the other direction, it goes like this. So this is these are the light lines. This is the time axis. This is the space axis of this observer. Now you remember these 2 points were drawn at plus L0 and minus L0 on the constant time surface on this t is equal to 0 surface, right? Now what happens to these points? Where should these points go? These points will go on the constant time surface, which is this surface, right? This is the constant time surface as seen by O prime. This is the constant time surface of O as seen by O prime, right? But are these 2 points at the same time? Are they on the same time surface as seen by O prime? Right. So if you look at these 2 points,
No.
they are not, right? Because you can see that this point corresponds to this time, and this point corresponds to this time. Right? So as seen by O, these 2 events are simultaneous, right? But as seen by O prime, will these 2 events be simultaneous? No. Right? There will be some time interval between these 2 points, which will be given by some delta t. First of all, I just have to use the Lorentz transformation. Now the Lorentz transformation tells me that let me write down from the perspective of x prime, x is equal to x plus v naught t times gamma, t prime is equal to t plus v naught x by c square times gamma. Okay. Now, what are the coordinates of this point? The coordinates of this point are L0, comma 0 and minus L0, comma 0 as seen by the O frame of reference. Right? So as seen by the O frame of reference, what are the coordinates? Plus L0, comma 0 and minus L0, comma 0. This tells me that those 2 points are at the same time as seen by O. I can now use the Lorentz transformation to calculate x prime and t prime for each of these points. Right? So I'll call this x1 t1. I'll call this x2 t2. Here I will get x1 prime t1 prime. Here I will get x2 prime t2 prime. What is x1 prime going to be? Well, I can just put this equation. I can just put x1 and t1. x1 is L0 and I get some gamma factor. What about x2 prime? x2 prime, same thing. T is 0, so I get minus L0 gamma. So what will this, the first thing is L naught gamma and minus L naught gamma. What about T1 prime and T2 prime? I use this equation. So T1 prime is, now you see T is there, right? But T is 0 for both points, T1 and T2. Now, if this was a Galilean transformation, remember there would be no X, right? T prime would be equal to T. There is nothing to do with X. Position will not
No
come in.
change. Yes, sir.
But here the position comes in, right? So what is T1 prime? T1 prime becomes V naught by C square, gamma V naught by C square times L naught, and T2 prime becomes gamma V naught by C square times minus L naught. Right? So what happens? Let me just take this, all of this, shift it a little bit to the right, like this. Yeah. So the time for the first flash as seen by O prime will be gamma L naught V naught by C square, and this will be minus gamma L naught V naught by C square. And what is the total time interval between the 2 points? The total time interval will be 2 gamma
2 gamma L C naught by C square.
L naught V naught by C square. All right. So I will leave it here. So this tells you that the notion of simultaneity, this is called the relativity of simultaneity, which means that whether or not two events are simultaneous depends on the frame of reference of the observer. Okay. So I think this is enough for today's class. I'll give you an exercise so that you have something to do before the next class, which is that exercise show that for any two events, okay, so x1 comma ct1 and x2 comma ct2, the space-time interval. What is this quantity? Space-time interval we'll define as delta s squared is equal to delta x squared minus c delta t squared. This is the space-time interval. Okay. It remains invariant under a Lorentz transformation. That means that when I write down the coordinates of my events as seen by the moving observer or in the different frame of reference, right, then I can calculate from this delta s prime squared, which is going to be delta x prime squared minus c times delta t prime squared, right? So what you have to do is show that delta s prime squared is equal to delta s squared. It's a very simple exercise. You simply have to use the equations for the Lorentz transformation. You just have to put for this x1 for x and t, you just have to put these expressions with the correct values of the subscripts 1 and 2 and calculate this. You expand all the terms things will cancel out and you will get the same expression as before the Lorentz transformation. Okay. So I'll stop here. Are there any questions? Questions?
No, sir.
Okay. All right. So I'll stop the recording, and I hope that all of you